I'd like you to welcome Matt Belvedere, who's talking today about bitsquatting.gov.au domains, exploring network data bitflips in DNS traffic. Thank you, Matt.
Test. Oh, thank you. Can you hear me? Does this work? No? Do I talk like this? Does this work? Is this better? Okay, awesome. Cool. So, I've got an AV set up. I think it works. Awesome. Let's start then. So, I guess we'll start with the obligatory who am I, like a sort of a preamble of what decisions we made about our testing. The approach we made. We'll do enough 101 to explain how DNS works. I'll go over our setup and what that looked like. We'll go for an analysis of what the data looked like, some of the offensive applications, and we'll wrap up with a handful of conclusions. Awesome. Cool. So, this is the obligatory who am I slide. My name is Matt Belvedere. No relation to the popular vodka brand. I've been a penetration tester for over 10 years. I can be described as a professional cheeky individual, which roughly translates to I get paid to be a pest. I'm a co-founder of a small penetration shop named Proactive Labs, based in Canberra. Unsurprisingly, we do pen tests. This talk isn't about pen tests or penetration testing, but if you could get this put in scope for a gig, I think it'd be pretty funny. But starting off, before we go anywhere, it's important to know that we didn't exploit anything in this case. There's no O days. We did as much as we could with as little interaction as possible, other than serving a response to DNS. This is a key decision to not mess with the end machinery. Given the domains, I think that might be a defendable position, and an understandable one perhaps. But in short, the too long didn't read edition. Bitsquatting was disclosed in 2011 by a guy named Artem Dynaberg. It's kind of like typo squatting, except the machine is the source of the error, not a human. But the end result is a machine makes an error when trying to resolve a domain, and instead resolves a different domain. The error rate's higher than what you'd expect, and you see flips often enough that it's actually worth noting at some sort of scale. What our goals were for this was fairly simple. We wanted to recreate, or at least validate, part of the prior work from Dynaberg. We didn't want to catch connections, serve content, or interact with sort of machinery at all. That means we have some limitations, which I'll go over later. But ultimately, we wanted to get some real data and see what would come out of the sort of process. Prior works. So again, we didn't discover this. It's been in the public literature for a while now. Bitsquatting was initially coined by Artem Dynaberg in DEFCON 19, so that's 14 years ago. His initial proof of concept, he was catching all kinds of goodies. So that's things like core dumps of Windows machines, cookies, creds, a handful of other sort of interesting bits. Schultz had a follow-up talk in 2013, which had a heavy emphasis on HTTP. So that was doing things like taking advantage of flips in URLs, so like a O to a /. This is before SSL was sort of ubiquitous. Let's Encrypt wasn't until slightly later. Although SSL doesn't really matter for these cases anyway. Ed Miles in 2018, which he had about 30 domains and was getting 25,000 requests a week, just for idea of scale. He noted a lot of the requests appear to be from Google, and he suspected that's from the Quad 8 resolvers. Makes sense. And then more recently, two individuals, one, I can't pronounce his name, but Stoke, and Juno at Black Hat 2024. So they did quite a lot more offensive stuff where they decided to register domains for a bunch of common SaaS platforms and captured a lot of creds. We didn't do that, so we wanted a more passive approach. Don't at me, ACSC. Cool. Easy. Cool. So we'll go over some brief technical 101s this talk. So things like the internet, or at least enough to understand how the architecture works. DNS, bitsquatting, and some general overviews of bitflips. This is the briefest slide. Give me a sec. Tasty. So, internet abridged. Internet as a whole is a bit too big to cover, especially before lunch. But the key points are, it's a lot of interconnected networks, there's a lot of different tiers and providers. They're mostly interested in consumers who are using tier threes. In most cases, those providers have DNS servers, which their customers use. And thanks to Cloudflare for the diagram, because it shows us pretty easily. So, practically speaking, you've got a customer using an Australian provider, such as Aussie Broadband. You've got some public documentation, which on what their name servers are, ending in 142 and 242. And we can verify these are users are now testing setup by reading the applied configuration. Practically, that's me SSHing to a router and reading etc resolve. So given that we've got a given a network with a given provider, and we know what DNS servers it uses, and we have logs for upstream servers, and we know what our bitflips are, and we know that we've queried at least once manually to verify our logging works, we should be able to see this in our logs, right? Well, no. Which is interesting. And why is that? To understand that, we have to understand how DNS works. So in the early days, there are things designed and documented in requests for comments, or RFCs. RFCs, in this case, it was made in 1987. There's amendments and further documents, but they're mostly irrelevant. But in short, DNS initially had records, resolvers, and name servers. Records are what you would understand pretty typically. Think you A, quad, like NX records. Name servers, so that's the thing that serves your domain. So that's the thing for zone files, bind, etc. But there's a lot more nuance to the sort of server part that they describe initially. Practically, though, an application in your machine tries to resolve an IP address. So that's something like making a call for a get out of info. That usually talks to a local resolver in client. Most of the time, that's going to be system D resolve D on like a modern Fedora box. This is forwarded onto a recursive resolver, usually in a network. It's also your router in most cases. That's forwarded upstream to a series of recursive resolvers, usually provided by your ISP. This will query a DNS root server. There'll be a top level domain server, and then that'll query your authoritative domain server for your domain. So there's a handful of little bits pieces going on. But awesome. Okay. A lot of this doesn't really matter for what we care about. Just know that the thing you point to points to something else, and eventually it'll talk to a root server, top level domain server, and then our control server. Again, we know that our resolver is using other resolvers. So we're going to figure out what resolver was the last hop, so to speak. So we're going to figure out some level of attribution. So privacy nerds have been on this sort of stuff for a while. If you're familiar with DNS leaks, same sort of thing. There's a lot of websites we can use to figure this out. So one pictured there. We don't see any of our routers upstream resolvers, but we do see some other upstreams, if that makes sense. And there's 3 IP addresses of note that we care about, 119, 119, and 180. Well, we're starting with at least. Ignore the IPv6 ones and ignore the Google provided ones because that's systemd resolve default falling back to Google DNS. So double checking. One of those IP addresses looks like it's owned by Aussie Broadband. That's in reverse DNS, that's really sensible. Do we see this in our data? And practically, yes. So that's a good sign. So the reason I'm covering this is because we want to understand more about what's actually making the bitflips. But given that we're only catching sort of the last thing that made the request, you might not be able to tell what actually was the origin of it. You might be able to get a rough idea of what the provider is in some cases, but if it's using Quad 8, you might be out of luck. Yeah. Again, attribution kind of matters in this case. Like we want to have an idea of what the requesting software was, or in some cases, we wanted to serve a different. If you wanted to serve a different result or process data differently in some matter, if you're doing this against an organization and you didn't want to like steal creds from third parties who use it, you'd be out of luck in this case. But practically speaking, the origin's a bit hard to determine unless you're getting requests. Cool. So moving forward and recapping again, that bitsquatting is just passive DNS hijacking, and the machine's at fault, really, not really an end user. How this happens? Well, major culprits, mostly memory errors, usually bitflips and RAM. Single bit errors are probably the most common ones that we care about. Changing a 0 to a 1 ends up it gives you a different output. Issues come down from heat, power, radiation, etc. We've got some data to show correlations between solar activity and bitflips, which I thought was kind of cool. And other events that have been known to cause bitflips, radiation in general. So that's, if anyone remembers KiwiCon, maybe 2018-ish with, what was his name? Peter Gutmann, Dr. Gutmann, I guess, had a demo where he had a source of radiation next to an Android phone and the thing crashed after a couple of minutes. Other things that we care about. Age of hardware has a strong correlation of faults. This came from a study called DRAM Errors in the Wild, which is a large field study, which came from Google. That image on the side is a bit cheeky, but knowing that the age of machines generally has a correlation with how many faults it has. If you're using F-Droid, I believe that was a yeah, they had an issue where the build system couldn't build software anymore due to it not having a certain instruction in the CPU set, which was made in like 2006. So those are probably old enough to maybe be a problem, depending. Voltage also causes memory issues in a lot of cases. This is another sort of a cheeky slide, but in Adelaide, mains goes up above 260 volts. Also seems to go a bit north of that sometimes as well. The maximum accepted voltage should be about 253 volts, which gives you an idea of how bad that might be. But a quick primer in bit flips. So let's say we've got a given string ending in .gov.au. Let's say we do a single bit flip error, perhaps in the byte that's holding the O. That has changed the least significant bit from a 1 to a 0, but it can happen in any part of the bit, obviously, or any part of the byte. So in this case, that little red text there from an O to an N is what we care about. So applying that to our use case, the result of the string ends in .gnv.au. That memory is then used, the lookup happens, but it's the wrong domain. And this is the majority of errors that we care about, or at least for the purposes of this talk. So, in 2022, the .au TLD was made available. So that meant you could register domains such as foo.au or bar.au. It also means you can register domains such as .gnv.au or geo6.au. So that's what we did. We registered 2 domains. There's a couple of flips that I've just listed up there of what you could possibly use, but they were already taken. We didn't report that, but I don't think anyone cared. But that's, I guess it's not recorded for a reason. So in our approach, we can't really determine where the errors really happen, but in earlier approaches, such as Dynaberg in 2011, he put forward there were 2 paths to this happening. So either a DNS path or a content path. So that was either an intermediate resolver misbehaving, or content issues where it was most likely a DRAM error on an end user device. But practically speaking, the way they compared it was if the host header matched the original domain, so given an inbound HTTP request, the corruption happened on the red path, which in their case is the original. But if the host header matches a Bitsquat domain, the corruption occurred in the blue path, which is the majority of these things. But practically speaking, if the host header is also bit flipped, then the call to verify the SSL cert is also for the bit flip domain, which could be a valid cert that you own as the attacker. So, might be handy. Practically where it goes wrong for bit flips, again, basically anywhere, and it's most likely going to be DRAM on your end client. It also can happen on things like caching intermediate servers, so CDNs. So there's a really good incident of this happening, I think, for a Facebook CDN, and it ended up serving, I think it was part of Dynaberg's research as well. But the point being, DRAM on devices, intermediate caching things as well. Kind of like a good caching sort of poisoning attack, but you don't really control when it happens. What this ends up looking like, though, ooh. Yeah. So from a defender's point of view, or at least if you're Elasticsearch or logs or something like that, or EDR perhaps, your client application needs to connect to foo.gov.au. The bitflip happens in DRAM. The client performs client performs a DNS request to foo.geo6.au rather than gov. The request goes out for geo6.au. Attacker sends a record for that. A victim passes out the ARA query, has an IP address, and then it will connect to that thing depending on what the application is actually attempting to do. In this case, the attacker could serve content or just catch things depending. The client apps may or may not be aware of their connection to the wrong endpoint. So about cert pinning or a few other little things, they might not even be aware. Again, that's kind of interesting depending on what your app is, because you might now have creds for something interesting or other effects. But from an attacker's point of view, you register a domain for a bit flip. Well, actually, you find a domain you care about. You calculate all the bit flips, so you sit there and just flip 1s and 0s. You filter out all the non-usable ones, so that's things that are either registered or have non-ASCII printable or just not valid for DNS. You set up a name server. You handle requests and you set responses. And depending on what you want to catch, you set up appropriately for that. So again, depends on what you're sort of looking for. If you think that you're going to get web-ish traffic, you'd set up a web server of some form, or you just blatantly run responder, depending. it's sort of important to note here that you don't get to pick the clients, you just get connections. And you probably don't know what the client application is or how the data is going to be used. You can make some guesses, but you don't really know. And again, TLS might not matter here because if the flip happens early enough, SSL validation passes too. Our setup was pretty simple though. As the attackers, we didn't really need anything too special. We didn't want to catch creds or anything like that. We were just trying to understand how often this happens really. So we use Amazon/Route53 as a name server, nothing custom. Given what we just want the logs, and we pump the logs straight into S3. So we're trying to do very little with, I guess, that part there. And the logs out of Route53, if you've seen these before, look pretty simple. You get a date in ISO 8601. You get a query name, a type, resolver IP, and the EDNS client subnet. The EDNS client subnet is kind of like a performance feature that practically gives you a better idea of where the end client might have been from. You end up getting like a /24 of what the request was, what made the request. We did parse these if we saw them, and you got some pretty good ideas of where things are coming from in some cases. But what I was just talking about. But practically speaking, we just have regular logs, much like what a normal resolver would have, because this is a normal resolver. And the bitflips are the sort of the interesting part we care about. Thanks, Jupyter Notebook. So here's some real data. So this is what we end up having. We filtered out a few different fields, but practically speaking, it's just a big table of requests, responses, and ASNs. You may recognize some of those domains. You can probably figure out what they are. But again, noting that ASN in this case isn't particularly useful. That's probably an end user trying to connect to a website that does something tax related. No comment. So eyeballing the data, the first results we had were in April 2024. That kind of makes sense, given that's when we set up the data collection. The last record was in the 24th of July in 2025. So we got about 226,000 requests. And before February 2025, this was at 139,000 requests. Why it's going up, I don't quite know. Monthly breakdown. So April being a very short month. Again, we started collection on the 23rd. The early months seem kind of uniform-ish. Then the later months have a bit more variance. But eyeballing it, you're looking at about 10,000-ish requests a month for just flips for 2 domains. Cool. So one of the busier months was October 2024. So it was a large spike roughly near the middle to end of the month. Even the lead up to this was a bit larger than normal, about 400 requests a day, then climbing to about 1,600 requests, which is kind of funky. So it turns out that on the 24th of October, there was a solar flare, which is an X3 class. And the way the classes work is that X is the sort of scariest one, and X2 is twice as bad as an X1, and X3 is twice as bad as an X2, for an idea of energy. But you end up with maybe 8 of these X series events every 11 years, which is 11 years of the solar cycle. Other sort of interesting dates that we had. So June 2025 had a large spike as well. So during this period, there was a rough average of about 400 requests a day again, but then it peaks to about 7,000, which is kind of funky. Yeah, again, like possibly unsurprising. That was a weaker flare, but I guess we were sitting in the right position as opposed to being on the other side of the world. I don't know. I think at this point in my analysis, the time zone was incorrect because I think it actually says the 17th rather than 16th. But if you go back a bit, it actually says massive angry error saying that I've dropped time zone information. Don't do that. So request types. So we've got a pretty simple table here. I've broken into 3 sort of segments. Otherwise, it's this long horizontal, well, this long vertical thing. We observed 89,000 A record requests, so like that's name to IP. That was the most popular kind of request we observed. The second request type we saw was MX, so that's serving mail server entries, and then after that it was quad A, So IPv6 and DNS key and text. DNS key was kind of unexpected, but I don't quite know what the deal with that is. For those who have a network defense background, this might look a bit odd, mostly because that's not the sort of the distribution you're expecting for what DNS should look like. So there are public DNS servers that publish their results of what their requests look like. So in their case, Vacana publish their sort of yearly summary of what they get. So they put forward that over half their records were A record requests, but ours was less than half. And then they were thinking quad A is 19%, but ours is at 10, and so on and so forth. I suspect this might be from the zones that we're interested in may have a slower uptake to IPv6 for their edges. Maybe. But I don't think this really indicates certain types of requests are more or less susceptible to flips. I don't think it just happens to be whatever it flipped. Quick hourly breakdown of this. So this time I've got time zones right, which is good. Then I made the graph in AST. So the rest of Australia exists, but I've just treated it like AST. We see a nice little peak at 10 a.m. and then this sort of second hump, which is a bit weird. But if we start filtering out things that are what we think from Australia, again, like if you remember the part earlier where I described finding where the client's originating from, it's actually kind of crap. So this may not be terribly useful, but we do see a lot less data coming from Australia versus from overseas, kind of. But we also note a lot of exits for Australian infrastructure geolocate to the wrong country, which is kind of funky. So that's stuff like Z-scalers, which seem to come to geolocate to US, but the latency time you're looking at like milliseconds to Sydney. So I think it's here. Origins again, so like breaking it down by country, US at the highest, followed by Hong Kong, Ireland, and Australia. I don't know what the Ireland one's about, but the geolocation's kind of flaky, so I wasn't too interested in figuring out what the actual deal was here. By ASN, so grouping by ASN's a bit better. We find a lot of data from Google, Amazon, and Cloudflare. Cloudflare is kind of weird because we couldn't tell if this is due to Cloudflare DNS or perhaps more interesting would be if it's the origin servers, perhaps trying to look to connect back to an origin. If it's the latter, that's kind of interesting, but it's probably the former. Weird origins. So Z-scales get used quite a lot in Australia. I only recently learned that they're a sponsor for the conference, so I'm not trying to bash them. They just get used. That's all this is. So we're trying to look for queries that have a strong chance of being internal. So like that stuff that like comes at what we think is coming from a client on a network. And the way I do that in this case is if you're familiar with Active Directory, yeah. If you're familiar with Active Directory, you may have seen this part of a DNS request internally if you're logging domain controllers. External clients don't usually make those requests. This is usually service discovery things like LDAP or Kerberos. So we're seeing machines that are on domains that end in .gov.au, bitflipped, and looking for Active Directory related domains. So we think this is service discovery for internally malfunctioning boxes trying to resolve authentication systems. If you're a pen tester, you probably have some ideas of what this could mean. And I think the intended, sort of breaking it down a bit more, this is what AD sort of related traffic looks like. So you notice the underscore for things like Kerberos and LDAP or site queries. So it gives you the name of a given site. Those names are intended to be human readable, which are often locations. You also see the victim domain names here, which I won't read out, but you can probably read them. So, yeah. What do we care about the origins? Again, like let's say you want to exploit this thing, you want to have an effect on the right system. If you're operating under a tightly scoped model, so like pen testing, attacking end users, so like third parties, you're probably going to get banned. But if you're not operating under a tightly scoped model, you probably still want to affect the only machines you care about, which might be internal or external ones, depending. I think if we break this down, we end up with traffic that's either general internet users, so it's ATO calculator people, general scanning stuff, which is probably explains why we see some non-resolving hosts, internal Active Directory systems doing service discovery, and I think that this might not have been covered as much in earlier works, so it's sort of applying bitflips to coerce authentication scenarios or system-to-system auth defensive apps. So, gone. So, Lovely. So good candidates for things. Getting creds. So again, stock, Juno, 2024, DEF CON. They were catching quite a lot of creds. I think system-to-system credentials are probably better to catch because there's probably no MFA or things like that we care about. Dynaberg was catching crash dumps. Stock was catching OAuth tokens. I think logging systems and metrics, telemetry, all sorts of stuff might be of interest if we can start getting flips of those. Or things that might get you RCE, so unsigned update services. Again, TLS side of it doesn't matter, the actual blob that you're delivering is. Existing tradecraft, so again, certainly exists. That was 2024. They got quite a lot of success. So that was 6.2 million requests over 4 months. They reckon they caught about 15,000 emails, which is kind of handy. We didn't go down that path again because that'd be bad, but like obviously this works for flipping. The non-obvious applications, I think, are things like turning these leaks into useful information, so such as determining internal services layouts, so from Active Directory sites, etc. I think there's a lot of things that are generally sort of unsafe internet protocols, which would be kind of interesting, so catching LDAP bind creds from shitty appliances, so like the Wi-Fi radius boxes, etc. Those embedded Wi-Fi access points aren't using ECC, so they're a bit more susceptible. Printers, etc., all that sort of embedded crap. Awesome. Okay, so from a recon angle again, you see a host, a domain. Sorry, where are we? Data center? Yeah, awesome. Yeah, so a site named Data Center. Not a fantastic example, but sort of ideas of what's going on. In this case, the ASN is kind of useful to know where it came from. I think that's probably high confidence that it actually come from that. Sites recon, again, this is probably a better example of a request for varsity lakes, which looks like it might be related. Who said that? Dear, oh dear. So I think learning of product affiliations is probably also a good angle here, perhaps giving sort of stronger evidence to correlate things. So in this graph, again, we're looking for AD-related comms for LDAP, and we see a lot of things coming out of Zscaler. It's kind of interesting. Sort of making it more practical. I think for Windows authentication, you know how if you're a pen tester, you've heard of coerced authentication, so NTLM relay, etc. I think there's a lot of angles where you could probably make a slightly better responder to bitflips, and that might be interesting. I don't think this has been done before. Like, we didn't do it. Again, that would be bad. Might be some future stuff that's interesting. Yeah, you could make SPF pass or other things like that. That might be of interest, but I'm getting a bit too close to the end of the report, end of this, so I'll hurry it up a little bit. So we did actually tell someone, or some places. Nah, that's right. Again, other questions that might be of interest. Are there sort of common platforms that still get deployed, or common tools that get deployed on shitty hardware, so like things that aren't using ECC, which bitflips could bite? Replicating TLS-enabled services like the stock work from 2024. Multiple bitflips are more interesting. Yeah, it's probably more researchy thing. How many places are using Z-scalers, and what if we started handling requests more gracefully? That'd be interesting, I think, as well. But practically speaking, they happen enough to be exploitable. You only really need one interaction to make a cheap domain worth it. And I think there's a lot of room for new and weird attacks. But we did have one other quick sort of observation that was funny. If you're familiar with how GetOut works, you may note that that says E not found. So one evening after as we're doing this research, I got pinged on Slack with an alert saying that our primary domain was down. So it's a company website. I don't really feel the need to redact this because that's exactly how I felt when it happened. So I went to investigate it, and yeah, it's a picture of me in the background of me. It's just on Slack, but fight me. So we do a quick host, like quick DNS request for our own stuff, and okay, we get results. But then when you use our upstream DNS as opposed to our servers hosting our name servers, it doesn't work. And what we noticed eventually was our domains, not just our bitflip domains, but our corporate domains, got seized. And the only thing they had in common was it's not like a non-attribution thing. Like they're real domains, like they're registered to an ABN, like the same contact details. But practically speaking, if you do this sort of research, you might get your domains yanked for every .au your ABN owns, which isn't great, especially given that ABNs are public. So I wouldn't say to do this. But yeah, exactly. Like if one was to register some domains with someone else's ABN and start violating the TOS, I think there's a word for this. Anyway, thanks.